So last day we ended our discussion on support vector machine. Today we will start entirely new technique of machine learning, that is, as you can see on the screen, artificial neural network. So what exactly artificial neural network is, before we uh, go the theoretical details of this discussion, let's start with some uh, practical question. So assume that we have a task to recognize a person, and forget about machine learning right now. Assume that there is no concept of machine learning present in a computer. So if I give this particular problem to a computer, how computer can solve this issue? You know, there can be several steps a computer can follow. Like, we can assume like there is lot of images stored in a computer, and you have an image that you want to check among those set of images which is stored in the computer, which is the image that is closest to the image that you have. So it's like the image will be fed to the computer. There will be some algorithm. That algorithm will take the images one by one, and somehow it will try to delete some specific feature and do some hard calculation. Hard calculation means, say for example, the difference between the eyeball, the length between the two eyeballs. The length is a hard feature, you can say. Means hard feature mean since we are not considering any concept of machine learning here, that means we are assuming that that particular image is stored in a computer and I want to identify. So somewhere I will find a particular image where the length between two eyeballs will be exactly matched with the length between two eyeballs of the image that I have in my hand. Something like this. And not only for length between two eyeballs, maybe some other features as well. So what you can see here, that it's basically to some extent just like a linear search. Linearly, one by one, the images are coming and it's checked various parts of the image with some hard computation. Now, what can be the time taken by the computer for this task? Naturally, if I consider that we have a lakhs of or crores of images, so in worst case, maybe it will take hours or even day, even with the fastest computer. But if you think the problem is given to you to recognize a person, how much time you take generally? You will say it's basically couple of seconds. Even if you have met that particular person few years ago, still mostly you can recognize that person within a couple of seconds. So from this example, it looks like a human brain is very faster than computer, right? But is it really true? Let's see. If you compare the traditional computer's IC speed with the speed of a human brain, we will see that the traditional computer's IC speed actually works in a order of nanosecond, 10 to the power minus 9 second, whereas the human brain works in say microsecond, I mean 10 to the power minus 3 second, in order of microsecond. So there is a huge difference between the processing speed. So from this particular value, it's very easy to understand that we are very slower than computer speed. But still, human brain is very faster for solving that type of issue compared to computer, right? So what we have observed, that although human brain speed is 6 order times slower than present IC speed, but human brain is much faster than computer. Now question is that why? Anybody give me? Okay. Question is that why? So the reason is that, in our brain we have special things, a special structural component rather, you can say, which we call neuron, which are massively parallel in nature. To some extent you can say that there are almost 10 billions of neurons present in a, you know in a normal human brain, where the total number of interconnections between the neurons is in order of 60 trillion. So from this data, I think it's very easy to realize that how complex our human brain is. And this particular thing, so that means this is actually the reason behind the very fast speed for recognizing a person or something like this type of task. So convinced by this type of, this particular data, if we, is it possible to implement the concept of neuron artificially for a computer as well? If we can do that, then automatically the speed of the computer will also increase for that type of task, right? But the neurons that we are talking about for human brain is a biological neuron. And if we want to implement or do something like a neuron, a biological neuron for a computer, we must have some mathematical formulation, because computer is a electronic device which follows, you can say, a sort of set of equations. And that mean the neuron that, the neuron that we can develop mathematically is basically artificial in nature, definitely, right? And the interconnections between those neurons creates a network, right? And that's what we call neural network. Since we are planning to mimic this neural network, the biological neural network, in some mathematical form, so that computer can utilize that, that's why that is called artificial neural network. So it's an artificial one, definitely, right? So before understanding how artificial neural network is, let's go through some, usefulness of the artificial neural network that we can have. So as you can see here, there are a lot of, points we can arise. We start with non-linearity. What does it mean? You see, already we have went through several machine learning use cases, and this linear and non-linear, this particular term is very, known to you now. In case of linear, in a very layman term, if I say, linear means there will be a linear relationship between the inputs and the output. As simple as that. Non-linear relationship means non-linear, problems mean that the relation between the input features and the output will be definitely non-linear. Interestingly, most of the real world problems are non-linear. So that's why, since artificial neural network is highly compatible for solving nonlinear problems, so it can be a very good option for us in future. Secondly is that we can easily have an input output mapping with form of error. The concept of error you already know, and obviously it's also a learning with a teacher. So we are still talking about supervised learning techniques. So, and also there is a very important thing that is called adaptivity. What is this? You see, as a human being, you can also feel that, like, you know, you are presently in a location maybe where mostly we have a summer part present. Maybe in future you will go somewhere where mostly winter are there. Lot of, the temperature can varies. Not winter, I will say. The average temperature may vary in another place. And if you go that in that place and start living in that place, all different biological activity will be adjusted accordingly, right? And similarly, human brain as well. So we have a very highly adaptive nature in our brain and our body, so that we can adjust in the environment where we are residing. A similar thing happens with artificial neural network as well. Based on the data that you are providing to learn, it's very easy to adapt the free parameters which is going to be changed to adjust with the new dataset to make much better model. And I will say the fault tolerance is a very crucial thing. What is fault tolerance? It is saying that failure of very few neuron or connections should not collapse the whole system. As I told you that we have a very close interconnections between neuron. Since close interconnection is there, that means from neuron 1 to neuron 2, it's not a only dedicated path is present. We have a various paths from neuron 1 to neuron 2 you can go. So among n number of paths, if one or few paths anyhow disturbed or have some failure, it's not going to hamper the whole system because the data will flow through the other paths. A similar thing can happen in artificial neural network as well, because we are basically implementing the same biological neuron artificially, mathematically for a computer. And since that means we are basically doing some mathematical operation or some mathematical formulation, we are representing in some way. How we are representing, that I am coming very soon. But since it is a mathematical formulation, so it's very easy to create a VLSI, chip which can do the same. You will see in market lot of, mostly you will see that lot of devices are available where VLSI chips are present, which has a capability to to do some lot of predictive task, some AI related task. The only reason is that since the mathematical formulation is very easy to implement in a VLSI, that's why it's possible. Anyway, so we have discussed some usefulness and capabilities of artificial neural network. Now let's first try to get the motivation of artificial neural network from a biological neuron. We already have an idea of biological neuron. We have went through the concept in our school days, I hope so, but still, just for time being, it's time to refresh those knowledges in a very brief way, So that's why I have given this particular point to you, that let's go through this neurobiological analogy of a biological neuron. As you can see in the left hand side, this is a schematic diagram of a biological neuron, right? And this, if you closely watch a particular neuron, I mean this whole thing as one neuron, right? If you closely watch this neuron, you will see that there is three parts mainly. In one part, it accepts the input from other neurons or some inputs. For example, over here, it accepts the input. I'm sorry, it accepts the input from here, maybe directly from some input or input sensor or from other neurons. Anyone is possible. And after accepting the inputs, it basically refers to a part which biologically we called axon, and we have a nucleus here where some data processing task happens. And after processing the data, that output gets transmitted to other neurons or maybe the output sensor of our body through the output parts, which we call brain right. Oh, I'm sorry, I had a mistake. I started with this. We take input from brain right, we process this and then pass the signal to the other neurons or maybe some other output sensors. I'm sorry, brain right is the input part of the biological neuron. Anyway, whatever it is, but as a result, you can say there are three parts: one input, processing part, and output, something like this. Now, if I want to represent the similar thing with for creating some mathematical formula, the schematic diagram will look something like this. Just to understand how we are doing this, I have kept the biological neuron in the left hand side as a reference, and as you can see, we have some inputs. So just assume we have some inputs over here. These are the inputs. Just like we have several brain rights, more than one input possible, so that's why I have more than one inputs here. Okay. Now, these inputs are basically flow through this particular line and comes here, which is basically, you can say to some extent, the nucleus of the neuron. So this circle is representing the nucleus of the biological neuron, which is presented here. So that means some calculation will happen here. Okay. And then based on the calculation presented in nucleus, the output, some output in some form is traversed through this axon and transmitted to the other neurons. Just for time being, I'm not considering any other neuron in my model. I'm considering that I have only output flowing through output. So the box, the black box that you can see, it's, you can say, a function which takes all these inputs as the parameter and process something, and then the output flows through this part. So what I have discussed here is in a very layman term, you can say, like I'm saying some function. What is a function? I've not yet discussed. What is the definition of the function? I'm saying that there is some calculation happening here. What calculation I'm happening? Still, I've not described that. But before I describe these two parts, one thing you notice here, we have some W's present. What is this W's? These W's are actually, you can say, the free parameters. And how it is useful? The usefulness is that, say for example, in a biological neuron, if you assume that, you see this particular neuron is connected with many other neurons in the close interconnection. So the inputs that are here is not floating. These inputs are actually output of some other neuron. That means continuously this particular neuron is accepting input from various other neurons, right? Now definitely, depends upon the task that you are going through. All these out inputs that is accepted by these dendrites may not be important. Maybe the inputs from this neuron, sorry, this dendrite, and this dendrite is important, but others are not. So how to represent this importance mathematically? That's why you have represented these w's. So by adjusting the value, some value in this w, we can actually regulate the importance of the inputs of these neurons. The inputs actually, you can say. Say for example, if I write wji equal to 0, it means that I am not at all bothering what inputs I'm getting from x1. Or if I put wji equal to 100 or maybe something more than that, it means that I'm giving much importance on this x1 and maybe some less value here, so some less importance to the other inputs, right? Now question is that who will decide the value of w's? You are not going to decide this. These values will be adjusted automatically based on the input output understanding during learning of this particular model. How it is possible? When we will implement that, and maybe in future when we will derive, we will be able to understand. But just for time being, understand the necessity of this different variables or whatever you can say. Similarly, we have another thing, that is bias. Just like you can say the intercept for a straight line, and not intercept, the yes, intercept for the straight line, that's b. Okay, so what mathematical calculation we can do over here? What we can do on a very straightforward method, we can simply do a summation of the x1 and w1, multiplication of x1 and wj1, then x2 multiplication of x2 wj2, x3 wj3, x4 wj4. We can do simple summation of all this, and obviously bias. What actually bias is, we will decide later. Describe or discuss later. Anyway, so we can do a simple calculation. So you see here, this wji is a connection between weights from neuron I to neuron j, and that's why I have written neuron wj1. What does it mean? It means I'm assuming that this is the jth output. Like jth output, I can have j plus 1th output as well, j plus 2th output as well. So I'm just representing one output represented by j, and this jth output is connected with the first neuron. That's why I have represented this as wji. Similarly, wj2, it's wj1, it's wj2, wj3, wj4. So that means I can say wji, and that's what I have written here as a uh, general term. You can say wji, connection between weights from neuron I to neuron j. So we have a neuron in this site, maybe. So that's the jth neuron, and these are the ith neuron. So through ith neuron, the jth neuron is connected in this way, like this. and the calculation that we are going through here is getting as output uj. So this uj you see I have written in this way. It's simply nothing but a summation, summation of multiplications between xi and wji. That means this input and the corresponding weight. Depends on the weight value, definitely we will have the importance of the xi will be adjusted accordingly. And as I told you that there is a bias, which in a very layman term I have written that bias of neuron J to introduce the non-linearity. We will see that in more detail. And then we must have a function. That function will basically takes this whole summed input and will give an output, some value. What value? That depends upon the nature of the function, right? So the nature of the function I have represented as something like a symbol. What I hope you can recall, this is a symbol of sigmoid function, right? So I have, just for timing, I have used the sigmoid symbol here. So that means the output, output means the output of this particular summer unit will go through the sigmoid function and it will give some output. So see, if it is sigmoid function, I hope you can recall the output will vary between 0 and 1, right? So this is a very basic idea of a single neuron, and this is what we call Mcculloch Pitts model. So this is the first ever model designed by Mcculloch and Pitts, which basically gives the analogy of a biological neuron in a mathematical form. Before we dive more on this part, we have to know what are the other activation function possible here. This is what we call activation function. Why it is called activation? Means its function activates the output in some way based on these inputs. That's why I call activation function. Now definitely the nature of the activation function will depends, how much it will be triggered to the other neurons. It will depend upon the nature of the activation function. So let's see what are the different type of activation function available for us. We will start with these 3 activation functions presently. There are many more, anyway, let's see one by one. The first one that I have written is a simple threshold function. It's just 0 and 1. That's all. You see, like output will be either 1 or 0. It's a simple biological, binary output. Depends upon what the input is. This Vi is representing the input. So if Vi is greater than equal to 0, that means this summer value is greater than equal to 0, output is 1. If summer value is less than equal to 0, less than 0, output is 0. That's all. A very straightforward activation function. Or there can be one more thing which we call signum function. What is signum function? It is actually doing just similar thing like threshold, but the the binary value changes here. Instead of 1 and 0, it is +1 and -1. That is the difference. Okay. Similarly, if we have a linear function means actually it's simply equal to output. Output is equal to input. That's all. That is what I have written. You see, y equal to Vi. That's all. You don't need to even write in this way, because whatever the value of Vi doesn't matter, output will be that one. So it's a linear function. If you can have some linear equation as well, but not non-linear. But by the way, whatever you have seen here, all are linear form. Let's come to some non-linear part. The nonlinear function can be, of different type, but we will discuss only three of them here. The first one is the sigmoid function, which already we have, experienced in logistic regression, right? And also the function definition. Similar like sigmoid function, we have one more function which we call tan hyperbolic function, which is, you see, the structure is very similar to the sigmoid, but the difference is that the range vary from +1 to -1 instead of +1 to 0 in sigmoid. That is the difference. So naturally, the expression of the function will vary, and this is the expression of the function. What it is saying? 1 minus e to the power -2 into input. The vi is the input. You see, vi means ith. I mean, I'm saying ith. Okay, vi means I should be in subscript. Anyhow, it's a mistake. So -2 into input divided by 1 plus e to the power, again -2 into input. So we have only difference between plus and minus here. That is the difference. And because of that, you will see that tan hyperbolic function looks something like this. And there is one more, a very interesting function that we call ReLU. The full form of ReLU is rectified linear unit. Okay. So the rectified linear unit mostly used in deep learning. We will see that when we will start deep learning, understanding deep learning in future. And the idea of rectified linear unit looks something like this. It's a mixture of linear as well as a zero. Like what you see here, the graph says that if the output more than 0, then it will look like linear. But if the output is less than 0, then I will keep it as 0. So the function definition looks something like this. Yi equal to Vi when Vi greater than equal to 0, otherwise it is 0. So there cannot be any negative value in case of ReLU. So you will see that in future, sigmoid, tan hyperbolic, ReLU, these will be very, commonly used activation function in different machine learning model. Other than these three nonlinear functions, there are some nonlinear functions I have not discussed here. When, if time permits, when we will encounter some problem, then we will discuss them. Just I am telling you the names here. Those are, you can say, one is pre-ReLU. In case of pre-ReLU, this 0 is not, as you have 0 here for v less than 0, it's not exactly in case of pre-ReLU. In case of pre-ReLU is like the curve will be somewhere like from here, like this. So that means if input is more than 0, then it's linear, output equal to input. But if input is less than 0, then it's not exactly output equal to input, but it is some function of output equal to input. That's why curve will not exactly in opposite order, but it's bit bifurcated, just like a refraction diagram you see in physics. And there is one more thing, one more activation function which we call softmax activation function, which gives a probabilistic estimate of some output. Okay, so in future, if we use, if time permits, and if a model demands this activation function, we will discuss more on this. So these are set of different activation functions we have discussed. Now let's do one thing. Let's start with understanding how we can use this artificial neural network for solving our simple tasks.